Hello everyone, today we're going to be doing logistic differential equations. Sorry for the weird spelling and the kind of swiftness of this video. My camera died in the middle of recording, which seems to be a running trend with these videos. I was really getting into it and that it just crashed and that made me so sad. But anyway, let's get into it. Logistic differential equations. So logistic differential equations are equations that relate to this line right here. Which is called an S-curve or a logistic growth curve, which is modeling something that those of you in AP Enviro like to call a specialist species, or a species that has limiting factors on its growth. So that's something that maybe, let's say you have ants in an anthill, and they're breeding, not breeding, but the queen is producing more, and they produce more and more and more, up to a point, because maybe there's a space is tough, maybe they're getting picked off by predators, maybe they're getting stomped on by some kid in the high school playground, in a elementary school playground, maybe these ants don't have enough food, and their population is limited by some sort of factor, right? Something is limiting this population. There's a curve on this. So that means that there's going to be an upper bound, which is called M, or the carrying capacity. Now, there's a couple rules about logistic growth curves, but let's talk about the only one you really need to know for the exam here, and that's that this point here, halfway up the curve, is going to be the maximum point of growth. So that's when your population is growing the fastest. That's when you're zooming, right? That's when this population is reproducing the quickest. And so that is always going to be always at the halfway point, when M is half, when you're at half the carrying capacity. This is always going to be true for any of these problems. So if they ever ask you, what is the carrying capacity, what is the carrying capacity, you find M, and what is the point at which, what is the population when the population is growing the fastest, is going to be half the carrying capacity, M over 2. And so these problems are formatted in very different ways. There are three main ways that they're formatted in, two of which appear very often and one that really doesn't, but I'll show you guys what all three of them are. So dP over dt is the first method, equals Kp times 1 minus P over M, where they have the m's, and these two will be constants, these two are numbers, because carrying capacity is a constant, and then this is the constant proportionality, which is just kind of a number in front of the p that dictates how fast your population is growing, basically how steep your line is, and that's going to be in front of the population value here. Now, dp over dt is essentially saying how fast is my population growing over a period of time, right? This is the derivative of this equation right here, dp over dt, in respect to time. So how fast is my population changing in respect to time? And now, they'll ask you a lot of questions about these, but the most common ones, and the ones you really only need to care about, are about, let's say, this value here. So they ask you, what is the carrying capacity of this population? And then they'll give you these values. They'll say, they give you this entire equation and say, what's the carrying capacity? Well, it's just going to be whatever values under the p, right? That's pretty simple. Now, another thing that they might ask you, though, is what is the rate of change of the population when the population is growing the fastest? What is the maximum growth rate of this population? And what you'll do is, instead of having to take the derivative of this and set it equal to 0, blah, 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 to find the maximum, all you need to do is take m, divide it by 2, plug it in, and then that's your answer, because your population is always growing fastest at half of the carrying capacity. So that's the first value. That's the first possible equation. The next possible one is very similar to this one. Very, very similar, except you'll have this. This is very rare. This one doesn't pop up too much, but if it does, you'll know what to do. Actually, this is just going to be something, I'll call it W. I just made these random numbers. But you'll have two numbers here, where this one is a value that is not 1, and this one is some other value. So if this is not 1, then you know that your carrying capacity is these two values multiplied. It's x times W is equal to your carrying capacity, M. And that'll give you your carrying capacity, and then you'll just take half of that to solve for the maximum rate of change, or for the population when your population is growing the fastest. All right, and then finally you have one more method that is entirely different from what you've seen before, but let's hope that we don't get too lost. So, and this one's one you've definitely seen before. P of t, or just P, your population in respect to time, your equation is equal to some value, m, that you're familiar with, divided by 1 plus AE negative KMT, I think. I know that doesn't sound very sure, but I swear I swear that this is it. I promise that this should be it. Sometimes you see it as negative KT. All in all, I can't remember exactly. It should be this. I looked it up online and it said that it's this, and then some say that it's KT. I remember being KMT, but if I'm wrong, please do not kill me. This should be the equation. This is the one that I remember from class. All right. So, what does this equation give us? You know, this seems very complicated. This seems very weird. This is nothing like the other ones that we've confronted here. And so, this actually has a fairly simple solution to it. This is something that's not all too complicated at all, and something that you'll definitely get into very quickly. Okay, so let's say we have it, regardless of whether or not we have an M here. What you'll find is they'll give us all of these values. You know, they give us M, they'll give us this thing here, and they'll give us an equation. Basically, all of these values are filled except for A. And then they'll say, when the population is 0, that at time equals 0, and when the population is 0, no. When the time is 0, the population is like 30, right? There are 30 elephants when the population is 0, and the carrying capacity is something like 50,000 elephants. What is the equation that models the logistic curve for the elephants? And the answer to that would just be solving this equation for A, because A is the only thing you're missing. You have everything except for this A value. And all you need to do is say, okay, well, when time equals 0, P of 0, you have 30 elephants, right? I'm just making this up. So you set this equal to 30. And you know that time is equal to 0. So this is just 0 times whatever you have here. And so this becomes 0. Anything to the power of 0 is 1, right? Even 0 to the power of 0 is just 1. So that means you have 1 plus A, and M, your carrying capacity, I said it was like 50,000. Cool. And now what you do is just simple flippy floppy. You multiply both sides by 1 plus A and divide both sides by 30. And you get 1 plus A is equal to 50,000 divided by 30. Subtract 1 from both sides. Sorry, minus 1. And then this is going to be your value for A. You plug it in, and then that would be your answer. So very simple problem, not too hard to get into. There may be additional forms that this equation takes that I may go over in review. If you even have review, people aren't really responding to my messages. But that means that you guys have a handle on the situation, so I'm hopefully useless. I hope so, because that means everyone's going to do well. But I hope everyone's doing fantastic on your coronation, and we will see everyone at hopefully some sort of graduation ceremony later down the line. All right, have a nice rest of your day, and see you all later.